Aqui acho que já está tudo certo, China.
Good morning, everybody. Welcome to Road2Paraty. This is a series of original talks organized by the Quantum Information School and Workshop of Paraty. So we're going to have the second part of the first episode of Road2Paraty. I would like to say a few words of this event. It's not for me to open the Road2Paraty. This is a road that was opened in 2007 by these guys here in this picture. So at the left, you see Professor Davidovich, who is going to lecture us today. On the right, you see Professor Daniel Jonathan, Ernesto, Steve, Marcelo França, Luiz Guilherme Terbar, and Marcelo Terra Cunha. So this is a series of Quantum Information School and Workshop that started in the city of Paraty in the year of 2007. And during the years, this has been organized every 2 years by a lot of people. So these are the guys who really started this road, putting really heavy stones in the roads of Paraty in order to make quantum information accessible to many students in Brazil and in the world. A lot of people worked on this school as organizers and also as professors and speakers. So this is the school of 2009. I will just show some pictures of the school. This is 2011, 2013, 2015, 2017, 2019, and this is the organizers of the current event. So we, instead of doing an online event, we thought to make these lectures once a month. So this is the first lecture of the Road2Paraty with Professor Davidovich. And during the 7 editions of our event, we've had many lectures in the school. So this is the list of lectures that have lectures in the school during the 7 editions. So without the students, this would be nothing. So we built this road in order for the students to take the road. So this is the group photo of 2009. This is the group photo of 2011, 2013, 2019. So this is the group photo of today, the people that is here watching us. So in Paraty, we dive into the quantum ocean. So it's common for us to have a boat trip during the event. So the event today is divided into an interview and into a lecture. So if you want to know more about the story of Paraty, you can go to our YouTube channel, subscribe to our channel, and then you will see the interview by Professor Davidovich, where you will learn more about this story. And then today we're gonna be lectured. We're gonna be lectured by Professor Luiz Davidovich. This is a short biography of Professor Davidovich. He got his degree in physics at the Pontifical Catholic University in Rio, Brazil. He got his PhD in physics at the University of Rochester. Then he became full professor of physics in the Federal University of Rio de Janeiro. He's member of the World Academy of Sciences, of the National Academy of Sciences of the United States, and he's also the president of the Brazilian Academy of Sciences since 2016. During his career, he got many awards. The last one of them he became emeritus professor at the Federal University of Rio de Janeiro. And his research is focused on quantum optics and quantum information science. He published more than 100 papers on this field. So these are some pictures of Professor Davidovich in Paraty. And we thank him very much for lecturing us once more today. So Professor Davidovich, please, you can start your lecture. You are muted.
So good morning, good afternoon. I don't know who are the people who are actually listening to this talk. It's a big pleasure for me to be here and to see actually former students and many colleagues here, hopefully in good health. And it's a special time for all of us, this pandemic time. And we must adapt and do lectures like we are doing now, virtual lectures. I will have to share my screen. I hope I am authorized to do that. Yes, I think it's going to work. Just to start, I would like to say that today is a special day in Brazil, or maybe all days now are special days in Brazil. But today is a day of protest against cuts in the budget for science in Brazil, severe cuts in science. And in fact, now, precisely at this time, 10 a.m. in Rio de Janeiro, São Paulo, Brasilia, we'll have a big Twitter manifestation. And I invite everybody to make their Twitters protesting against the cuts of science for science in Brazil. And we need really to do this in a very strong way because science is in danger. And the budget for science this year is extremely small, which means labs with severe problems, people getting destimulated, and science, not only science, but also innovation, suffering because of these cuts in the funds for science. Why they are wasted for other purposes. People, the government nowadays, the president, the minister of economy, don't care about science. And this is the reason why we go public to express our worries and our support for science in Brazil. So that being said, I would like now to share my screen and start this lecture. I wished we could all be in Paraty. It's a wonderful city, but I'm sure that we are going to recover from this pandemic. I'm sure we are going to recover from this very difficult political situation in Brazil, in which denialism goes together with these cuts in science. You know, science, truth, investigation, scientific arguments, they are dangerous for some people. And that explains partially why these cuts are being done in Brazil. So let me share my screen. I hope you're seeing that now. Okay, has this gone there?
Yes.
Okay, good.
Okay.
So I'm going to give you a lecture actually on an introduction to quantum metrology that's addressed to students who have not heard about this field of quantum information. And I hope to be pedagogical. I think we'll have time at the end for questions, so feel free to ask questions, and I'll be very glad to answer them. So this is the title, How Quantum Physics Can Help in Making Better Sensors. Below you'll see some names of financial agencies that have the purpose of helping science in Brazil. And you see also the logo here of the National Institute for Science and Technology in Quantum Information. So, you know, quantum sensors came from something imagined, from the imaginary axis to the real axis. We now have several kinds of quantum sensors being used for several purposes. There are industries and companies selling them, and also many labs still investigating the possibilities of using quantum sensors for several purposes. For instance, we can use a single atom to map the structure of a biomolecule in a very precise way. Magnetic sensors can be used for brain imaging, also with amazing precision. Gravimeters are being sold now, actually. They are based on atom interferometry, and they can be used, for instance, for surveying underground water and oil. Actually, if they are put in a satellite, they can even measure the amount of water in the ocean and how this changes due to climate changes, also in a very precise way. Gyrometers and accelerometers, quantum gyrometers and accelerometers are so precise that, for instance, submarine, if you know the initial position of the submarine, you can trace the final position without using GPS, just following what the gyrometers and accelerometers are showing you. And that can be done with present devices that are being built and commercialized as well. Atomic clocks have reached an amazing accuracy at the level of 10 to the minus 18. You can look at this paper in Nature this year, which shows this amazing accuracy of atomic clocks. These are atomic clocks developed at the National Institute for Science and Technology in Boulder, NIST. Of course, quantum physics and quantum metrology has been applied also to the LIGO gravitational wave detector, where they are using now squeeze states of light. And I'm going to tell you what squeeze states of light are in a moment. Now, all of that involves parameter estimation. And this can be used, for instance, to find the depth of an oil well using sound waves. So you just measure the time it takes for the sound wave to go there and then back. You could be interested in the time duration of a process or in a transition frequency of an atom. And this title that you see there, Optical Clocks and Relativity, that was a paper published in Science in 2010, shows how the transition frequency of an atom changes because of relativity when you displace this atom in the gravitational field of Earth. So a distance of 33 centimeters implies relative difference in frequency of the order of 10 to the minus 17, and that can be detected, which means that you can actually use that to confirm general relativity, which says that the time duration depends on the position of the object of the clock in the gravitational field. You can actually use parameter estimation to estimate weak forces or small displacements, phase shifts in interferometers, and as I mentioned before, detecting gravitational waves in LIGO. There is also another side of quantum metrology, which is a conceptual side. So the question is, what's the meaning, for instance, of the time-energy uncertainty relation? Well, Heisenberg dealt with this problem a while ago, and you see that in his paper on the uncertainty principle, it has a commutation relation between an energy operator and a time operator. And from that, if that was valid, you could get this uncertainty relation between time and energy. However, Pauli showed later on that you cannot have a time operator in general. That would imply a boundless Hamiltonian. So this original argument by Heisenberg does not hold. Also, people talk about the number phase uncertainty relations, which would imply, say, defining an operator for the phase, and this has been done by many people. However, if we deal with quantum metrology, we see that it's really not necessary to have an operator for time or a phase operator, you can actually derive these uncertainty relations using arguments from quantum metrology. And all of that, especially the second uncertainty relation, is also related to some very old papers with the participation of a great experimentalist, Len Mendel, where he mentioned that, finally, our work suggests that for purposes of making connections with experiment, the choice of the proper dynamical variables for the phase ought not to be divorced from the measurement process that generates the ensemble of measured values. So he was actually putting in question, he was questioning whether a phase operator would make sense at all, or whether the definition of this operator should depend on the experimental conditions. Again, quantum metrology does not worry about a phase operator. It derives an expression like this one from quantum metrological principles without the need of defining a phase operator. Now, let me start by reviewing what is a coherent state and what's a squeezed state. So a coherent state, for instance, of a harmonic oscillator is a minimum uncertainty state. So the product of the variance in the momentum with the variance of the position in normalized way, so that P and Q are dimensionless, is equal to 1/2. So if you want, I'm setting H bar equal to 1 here. Now, a coherent state of a harmonic oscillator is an eigenstate of the annihilation or the lowering operator A. And of course, this operator is non-Hermitian. So its eigenstates don't have to be orthogonal. Eigenstates correspond to different eigenvalues. It also follows from this expression that the average of this operator here, which is called the number operator, is just the average excitation of the harmonic oscillator. And this is equal to magnitude of alpha squared. Alpha is the amplitude of the coherent state. Now, all of that applies to a harmonic oscillator, but it can also be applied to the electromagnetic field if you consider that a mode of the electromagnetic field behaves like a harmonic oscillator. Now, we can also define a displacement operator, which when applied to the ground state of the harmonic oscillator gives me a coherent state of the harmonic oscillator. It's interesting that coherent states were introduced by Schrödinger just to answer some doubt which was raised about his work on harmonic oscillator. People saying that, come on, I mean, you have these eigenstates of the harmonic oscillator, and they do not behave like a particle oscillating in a harmonic oscillator. So Schrödinger showed that a coherent state would behave like that. And a coherent state is not an eigenstate of the harmonic oscillator. It can be written as a superposition of eigenstates of the harmonic oscillator, as you see here. And from this expression here, you can show that the magnitude squared of the scalar product of two coherent states corresponding to two different amplitudes is given by this expression. Therefore, alpha and alpha prime are not orthogonal in general. Okay, so their scalar product is given by this expression here. So a coherent state can be represented in phase space. Again, I'm using here dimensionless momentum and position. And we represent it by this ball here, using the fact that delta P, delta Q is equal to, the product is equal to 1/2. But furthermore, delta Q is equal to delta P in a coherent state. So the two, the dispersion in position is equal to the dispersion in momentum. And that is valid for any angle you have here. So if you have if you rotate the axis here, this is still true that the variance along one of the axes is equal to the variance along the other axis. Now, this is usually called the amplitude quadrature. It's along this vector here that defines the position of the coherent state, and the phase quadrature is the orthogonal one. So this is the representation of a coherent state. Now let's talk now about squeezed states. Well, again, using a phase space representation, a squeeze state is a minimum uncertainty state obtained from a coherent state by a scaling transformation. So you squeeze a quadrature like this one, and you stretch the other one so that the product of the two uncertainties is still the minimal, has a minimal value. That is, the product of delta Q times delta P is still equal to 1/2. Now, a squeezed state can be obtained from a coherent state by applying this transformation here. You see this transformation is nonlinear in the operators A and A dagger. And psi here is a complex number. It can be represented in this way. R is the amplitude of this complex number. Theta is the phase. And if you take psi real, so that theta is equal to 0, the uncertainties in Q and P are given by these expressions here. You see, you squeeze delta Q and you stretch delta P by using this exponential here. And setting psi real means that this ellipse here is along, say, the P axis. So the uncertainty with respect to Q is smaller than the uncertainty for a coherent state, but the uncertainty with respect to P is larger than the uncertainty for a coherent state. So for the sake of metrology, the squeezed vacuum states are more relevant. That means that you apply this transformation here to the vacuum, or if you want, the ground state of a harmonic oscillator. And after doing that, you can actually calculate the average number of states, or photons, sorry, in this state here. And you find that the average number of photons in the squeezed vacuum state is given by this expression, hyperbolic sine squared of R, which means that the squeezed vacuum is really not a vacuum state. It has photons in it, but it has excitations in it, if you think about a harmonic oscillator. And the average number of this number here, which is the number of photons or the number of excitations, is given by this expression. Okay, so these are squeeze states, and squeeze states are very useful for several purposes. Now, this is just a picture of what I have just said. So coherent state versus squeeze state. Now, if you displace the coherent state by a distance x, you see that you have some uncertainty in defining this displacement, and that uncertainty is due to the superposition of the new coherent state with the old one. So you don't have very good precision on the position, on the new position of this coherent state. And in fact, the uncertainty in estimating the displacement here is given by the width of the coherent state, which is given by this expression as I saw before. Now, if you have, on the other hand, a squeeze state like this one, it's aligned along the p-axis, and you do the same spatial displacement on the squeeze state, you see now that because of the squeezing, they are separated, they are not superimposed. So the uncertainty in the estimation of this displacement here is smaller than it was before, and it's given by the width of the squeeze state, which is now given by that, where R is in factor. So you see that if you want to estimate displacements along the position, for instance, axis, it's better to use a squeeze state than a coherent state. It gives you a better precision on the estimation of the position. And precisely because of that, squeeze states are being used in the LIGO interferometer. You also see from this discussion that precision of estimation is linked to the distinguishability of the two states. These two squeeze states here, after this displacement x, are more distinguishable than these two coherent states that have undergone the same displacement. And why am I so interested in estimating a displacement? Well, suppose you have a force applied to a harmonic oscillator. Then if you want to estimate the force, you can estimate it by estimating the displacement it produces on the harmonic oscillator. And that shows immediately that it's better to deal with squeeze states if you want to estimate the force than working with coherent states. Now, a recent paper made use of this advantage of squeezed states. And that was done by the group of David Weiland. It was published in 2019 in Science. And their idea was the following. You start with an ion in a harmonic trap. So the initial state of the ion is just the ground state of the harmonic oscillator. You know, from quantum mechanics, you know that in the X space, it's a Gaussian. In this phase space here, it's just the vacuum state or the ground state. It's a special case of coherent states when alpha is equal to 0. And now you squeeze the state. And we apply that operation that I mentioned before to this ground state. So now you have a harmonic oscillator in the squeezed ground state. And now you displace the state by using the displacement operator I mentioned before. So you get this squeezed state here, which is displaced with respect to the displaced ground with the squeezed ground state. You see here it's around the origin of phase space. Here it's a little bit displaced. And now what they have done, they apply an anti-squeeze operation on this displaced state. And by doing that, they go back to a coherent state, but with an amplitude multiplied by this squeezing factor here, e to the exponential of r. So you see, the whole thing can be written like that. You start with the ground state of the harmonic oscillator, you apply a squeezed operation, then a displacement operation, and then you do an anti-squeezing operation. And I leave it as an exercise for you. It's not a difficult exercise, okay? It's a homework for students to show that the sandwich of the displacement operator between two squeezed operators is equal to a displacement operator, but with a larger displacement. So when you apply this to the ground state, you get now this new coherent state here, which has a magnified amplitude. So if you want to estimate the initial displacement, you know, this is a very useful procedure because you're actually amplifying the displacement in this way, and then you measure. And then you measure the resulting coherent state. In terms of a graphical image, you have something like that. You start with the ground state, you apply the squeeze operator, then the displacement operator, then the anti-squeezing operator, and then you measure. And this is the usual symbol for measurement that we use in quantum information, okay? So you see, this is quantum amplification of mechanical oscillator motion. And, you know, some people who have studied amplification before might find this strange. They might think, come on, I mean, usually when you amplify something, you have noise. You know, we cannot do amplification without noise. But here, you know, you started with a coherent state, you displace it, and now you have a final coherent state with an amplified amplitude, and there is no noise. Well, the trick here is that you're really not amplifying the state. You're amplifying the displacement. You are amplifying the displacement operation, and this you can do without noise, as shown in this paper here, okay? So you see, that's an immediate application of what I have said before, and it's a recent application. You can use quantum physics to amplify displacements, and therefore that would help to estimate these displacements, even if they are very small. And if you estimate a displacement, that means that you can also estimate a force, even a weak force, applied to a harmonic oscillator. So you see quantum mechanics acting here and doing useful things for us. Now, precisely because squeeze states are good for estimating displacements, they are now being used in the LIGO interferometer, this amazing experiment, which was able to measure signals emitted by the collision of two black holes very far away from Earth. So they have an interferometer which schematically can be represented by this. So we have a laser field coming into the interferometer. There is a beam splitter here. So part of this laser goes up, part goes through the beam splitter. This is reflected several times between these mirrors, and then they interfere going through this beam splitter here, so you detect this interference. Now, besides applying this laser field, they are also applying the squeezed state, which helps to increase the sensitivity of this interferometer. Now, this was an amazing experiment. You know, because the arrival of gravitational waves affect the arms of this interferometer. You know, each arm has a length of 4 kilometers. Now, the arrival of a gravitational wave compresses one of the arms and enlarges the other one. So the differential displacement sensitivity is 10 to the minus 19 meters. So that's the difference in length between the two arms due to the arrival of a gravitational wave. Now compare this with the radius of a proton. Okay, this is 4 orders of magnitude smaller than the radius of a proton, and they are able to measure that. The relative change in this distance, that means this divided by the length, 4 kilometers, is given by this expression here. So it's a very sensitive interferometer. And in blue here, you see the increase of sensitivity by applying a squeezed state. So this was one of the first experiments where they applied a squeezed state to this interferometer. Now they have changed the interferometer, so they are now applying really a squeezed state, which allows to see even further away collisions of black holes. Now, parameter estimation in classical and in quantum physics follow the same procedure. We have a dynamical process, which depends on a parameter you want to estimate. You have a probe here. You take the probe in a given initial state. You choose an initial state for the probe. You send the probe to the dynamical process, and the interaction of the probe with the dynamical process depends on the parameter you want to estimate. Then you have a final state of the probe, and then you measure this final state, and you associate to each measurement of the final state a value of the parameter. So that's the general idea. Now we need some merit quantifier, and the one which is most commonly used is this one, which is the standard deviation between the estimated value of the parameter and the true value of the parameter. Okay? Now you might ask, come on, I mean, you don't know the true value of the parameter, you want to find out about that, so how can you calculate that? Well, fortunately, you know, in practically all the cases, you are dealing with unbiased estimators. What does that mean? That means that the average of the estimated values of the parameter over many experimental trials gives us the true value of the parameter. And that's not true only at the position of the true value of the parameter, also around it. That means this derivative here should be equal to 1. So that defines an unbiased estimator. And if this is true, we can replace X true here by the average value of the estimated parameter. And this gives me then the standard or the variance of the estimated values taken over all experimental results. So we're going to use this now as a merit quantifier. And it's clear that this estimator depends only on the experimental data. Okay, you make lots of measurements, you use them to estimate the value of the parameter, and then in order to find the precision or the standard deviation or the variance, if you want, you calculate this quantity here. Now, let me give you an example in optical interferometry. You have here an interferometer. These are mirrors here. This is a beam splitter. So you have here some small phase that you want to estimate. When you insert a field into the interferometer, well, part of the field goes through this upper branch of the interferometer, the other part goes through the lower branch of the interferometer, and then you get these two parts together, so you have interference between them, and then you measure, and from that you estimate this delta theta here. Now, remember that when we discussed the displacement estimation, we considered the distinguishability between the two states. And we saw that squeezed states are better for that purpose. Now here, again, in order to estimate the uncertainty in the estimation of delta theta, we should compare, say, some original coherent state with this phase-shifted coherent state that undergoes through this upper branch here. That would be equivalent to, say, sending a coherent state through this interferometer and comparing the part of the coherent state that goes to the upper branch with the part of the coherent state that goes to the lower branch, and therefore it has not been phase shifted. We compare the two. So this is a scalar product between them. And you can show that this is equal to this expression here. That's just a scalar product of two coherent states. And if delta theta is very small, we can expand this exponential and write this like that. So you see this scalar product here, the magnitude squared of that, can be written in terms of this Gaussian here. It's a Gaussian with respect to delta theta. And from that, we find that the uncertainty estimation is of the order of 1 over square root of the average number of photons in the state. Okay? Now, this square root behavior is called the standard limit for the estimation of the phase, also called the short noise limit for the estimation of the phase. So that's what we get with coherent states. Now, can we do better? Yes, we can. This was shown within the framework of ions by Bollinger et al. And within the frame of photons and light fields by Jonathan Dowling in 1908. So suppose now, instead of having a coherent state, you have this funny state here, which is called the noon state. You see the word noon here. So this is a state in which you have n photons in one of the branches of the interferometer and 0 photons in the other branch, but you don't know where these n photons are. So you actually have the superposition of these two possibilities, and this is the noon state. Now, as you have the state here, and the photons in the upper branch are phase shifted, then this state here becomes this state here. You see only the state which has n photons in the upper branch becomes phase shifted. The other one with 0 photons in the upper branch remains as it was before. So now the state is like that. And you can show that the average number of photons in this state here is equal precisely to n here. Okay, these n photons that are either in the upper branch or in the lower branch. So this state becomes this one. And now we can compare this state here with the original one. And that will give me some estimate on the precision for detecting delta theta. So we find this scalar product again between the original state and the transformed one. And it's easy to show that this is equal to this expression here. It's a cosine square of n delta theta over 2. And from that, you find that delta theta, or the precision in the estimation of theta, is equal to 1 over n. You can find that immediately, for instance, by looking at the value of delta theta that makes this cosine square equal to 0. And this is achieved when delta theta is equal to pi over n, because you'll have here a cosine square of pi over 2, which is 0. So you see, now the uncertainty in the estimation of delta theta is inversely proportional to n instead of being inversely proportional to square root of n. So for the same amount of resources, for the same amount of the number of photons, we get a better precision here. You also see that, again, precision is linked to the distinguishability of the two states. These two coherent states are less distinguishable than these two noon-like states. So you get a better precision here, okay? So there are important questions related to these examples I gave you. First question, what is the best initial state of the probe? Second, what is the best measurement procedure? So what kind of measure can we do that leads, for instance, to the scalar product between the initial and the transformed state? And we have already seen the importance of choosing a good initial state, because noon states are better than coherent states to estimate the phase. But this is a general question. And in order to answer these general questions, we need a general method, a general formalism for dealing with estimation of parameters. And this was imagined, it was created, proposed by these three guys there, Kramer, Rao, and Fisher. And this expression here on the left is the so-called Kramer-Rao bound. It tells us that the uncertainty in the estimation of some parameter x is bounded below by this expression, where n here is the number of repetitions of experiment. If you repeat the experiment many times, well, this gives you a better precision. Of course, this is not always possible. For instance, if you want to detect the signal coming from a collision of two black holes, you cannot keep measuring that forever. I mean, you have to measure it within a very short time. Now, there is this function here, f of x, calculated at the value of the parameter equal to the average value of the parameter. And this function is given by this funny expression here. Now, Pj of x is the probability of getting an experimental result j if the value of the parameter is x. And then you have this logarithm here of Pj of x, the derivative of this logarithm, and that gives me what is called the Fisher information. And the Fisher information can be written in several ways. You just can, it's easy to show that this is equivalent to this expression here, which is also equivalent to this expression here. This final expression, I'll come back to it very soon, I will see. So this is the Fisher information. And in fact, Fisher showed that this inequality here can be saturated. That means it can become an equality when the number of repetitions of the experiment goes to infinity, or if we have a Gaussian distribution. Okay, then even for a single experiment, this becomes an equality. Now, for continuous measurements, these expressions can be written in terms of integrals instead of sums. So the Fisher information is then given by this expression. Or if you want to transform this one into a continuous expression, you get this expression here, where now, instead of saying that J is some experiment, you have here continuous of experiments, and psi denotes some specific experiment that was done, experimental result, and corresponding to the value x of the parameter. So this is the Kramer-Rao bound, which plays a very important role in quantum metrology. Now, let's try to understand where the Fisher information comes from. And we can understand that in classical ways. In fact, what I have told you up to now is classical. There's nothing quantum mechanical about it. So suppose that we are measuring some parameter, and that leads to a probability distribution for the value of this parameter. For instance, here we have two measurements of the gravitational field done in two different regions of the Earth. One was in the Andes, some city there in the Andes, and the other was in the Arctic Sea. Well, the gravitation is different in these two places. And if you measure in one of them, you get some value, in the other, you get another value. And in fact, this has been known with a very high precision, you know. So this is the value of the gravity in this place in the Andes, and this is the value of the gravity in the gravitational field in the Arctic Sea. So important question, how much does the outcome distribution change by a change of the underlying true value of the parameter? You see that these true distributions are different from each other, and if they are sufficiently different, we can actually distinguish this value of the gravity field with this value of the gravity field, okay? If they are too much superimposed, we will not be able to say that the gravitation in the Andes is different from the gravitation in the Arctic Sea. So again, the distinguishability between two statistical distributions is very important for estimating a classical parameter. Now, we can define the distance between the two probability distributions in this way here. This is the so-called Hellinger distance, okay? And if we have this, you see, you take the square root of the probability distribution here and here, you find this difference, then you square it. I mean, you have to sum over all values of k, and this gives me the distance between the two distributions. K, of course, the set K is the set of outcomes, okay? They're represented by these balls here. So this is the definition of the distance. Now, if you square this and you consider that these distributions are very close to each other because the parameter has changed just by a little bit, well, it's a little bit like you were seeing here, but even closer if you want, then you can say that x prime is just equal to x plus dx, a small variation of the parameter. You can expand this as a Taylor series, and if you do that, you find that this distance is equal to this value here. Now you see, we have seen this derivative before. Just to remind you, here it is. So that's the Fisher information. Okay? So you see that the Fisher information shows up here, which means that this distance here can be written as the Fisher information divided by 8, because there is this factor here, times dx squared. So you see that in this framework here, the Fisher information is just a measure of the change of the probability distribution. Okay, so we can use the Fisher information to estimate how distant they are if you make a small change of the parameter. Now, of course, this is related to the uncertainty in the estimation of the parameter. If they are distinguishable, the more distinguishable they are, the larger the Fisher information is, and the better will be the precision. Because remember, because of Kramer and Rao, the uncertainty in the estimation of the parameter has a lower bound, which is inversely proportional to the Fisher information. Okay? So now we understand the Fisher information on classical terms. Also, you can write the Hellinger distance in terms of the fidelity, and the fidelity is given by this expression here. You see, this is the fidelity between two probability distributions. If they coincide, if x is equal to x prime, this is pk square. So square root of pk square will give me pk. If you sum over k, that will give me 1. Fidelity will be equal to 1. Otherwise, fidelity will be smaller than 1. And again, if you set x prime equal to x plus dx, you find the fidelity is given by this expression here, where again, the Fisher information shows up. And you see from this expression that since this here is dx squared, not dx, that square root of the Fisher information divided by 2 is the speed of change of this distribution, probability distribution, as x prime gets different from x. Okay? So the Fisher information is related to that, to the distinguishability between two distributions. Now let's go to quantum mechanics. Now in quantum mechanics, we define the same Fisher information as we had before. So this is the expression we had before. I'm just writing here the continuous case, but then this probability here, or this probability density, since it's in the continuous case, is expressed in terms of these operators here and the density operator of the system. So this is just the probability of finding some measurement result psi, if the value of the parameter is x, is just the trace of the projector corresponding to this measurement here in the density matrix of the system. Now, in general, these operators here don't need to be projectors. In general, they are positive operator valued measurements. The special case of this POVM is the case in which these are projectors, von Neumann projectors, but in general, they don't have to be like that. And they satisfy this completeness relation, which just means that if you integrate this over all possible values of psi, it gives me 1. So you have a complete distribution here. Now, of course, this Fisher information here corresponds to a given quantum measurement, because we are choosing a POVM here. Now, the ultimate lower bound for the variance is obtained by optimizing this expression over all possible quantum measurements. And that gives me the so-called quantum Fisher information. Okay, so that's the definition of quantum fission information. Is the fission information as defined classically, but of course, the probabilities are expressed in terms of a POVM, and you have to maximize it over all possible measurements. There is a geometrical interpretation of that similar to the interpretation we had in the classical framework. You find the fidelity between two density operators. Probably you are not familiar with this expression for the fidelity. Well, you know, if ρ1 and ρ2 are density matrices corresponding to pure states, this funny expression here becomes this one, which I think you are familiar with. That's the magnitude square of the scalar product between psi1 and psi2. So in general, if you don't have a pure state, you have a mixed state. That's the fidelity between the two states. That's called Buer's fidelity. Now, if you calculate the fidelity between rho of x and rho of x plus delta x, so a small variation of the parameter, and expand it with respect to the x, delta x, you find an expression similar to the one we had in the classical case. But instead of having the fission information here, you have the quantum fission information here. So that's the fission information maximized over all possible measurement procedures. So you see that the quantum fission information can be obtained from the fidelity between the two distributions by just expanding this rho of x plus delta x as powers of delta x. Okay, and again, as I mentioned before, you see that the quantum fission information is related to the distinguishability between states. You have this minus sign here. So the larger the quantum fission information, the larger will be the distance between this fidelity and the number one, which means undistinguishable states. Okay, so the quantum fission information is a measure of the distinguishability between states, and that's why it comes in that Kramer-Rao relation as a lower bound for the precision. So, question: how to get the quantum fission information? And this looks like a very difficult task because, come on, you know. You have to calculate the fission information, given some measurement procedure, and then you have to maximize it over all possible measurement procedures. So how can you do that? You know, we have to imagine all possible measurements and then finally find the quantum fission information. That looks like, you know, a hopeless procedure. However, there are ways of doing that. I'm not going to demonstrate that, but let me just tell you that there is a general expression for the quantum fission information, which is this one here. You have the density operator of the probe corresponding to some value of the parameter x. This operator here is called symmetric logarithmic derivative, and it is defined by this equation here. You differentiate the density operator of the probe that depends on the parameter x with respect to x, and try to write it in this way, and then you find what L of x is. Okay. Now, in general, this operator here is difficult to evaluate. Basically, in order to evaluate, you have to diagonalize the density operator. And if you have a system with a very large dimension or an infinite dimension, that may become a very difficult, if not impossible, task. Now, for pure states and for a unitary evolution of the probe, the quantum fission information has a very simple expression. It's given by this variance here of this operator, which is expressed in terms of the unitary evolution of the probe. Okay, so for instance, if this unitary evolution is given by a simple expression like this one, x is the parameter, O is an operator independent of x, and you apply this definition here, then you find that this operator h is just given by this operator here in front of x. If the unitary evolution of the the probe is given by this expression, then O is known as the generator of this change in the probe, okay, in this special case. Now, when this happens, if this is true, if the quantum fission information then for the pure state of the probe and for unitary evolution of the probe, so no noise in the system, noiseless system, then it's easy to calculate the quantum fission information. And the precision in the estimation of the parameter will then be bounded below by this expression, where again, n is the number of realizations of the measurement, the number of experiments, and this is the variance of this parameter h here. Now you see, this starts looking like a Heisenberg uncertainty relation, right? For instance, if this x would be the time parameter, this would be the uncertainty estimation of the duration of a process. And you see that this unitary evolution here is just the time evolution of the probe. So O is actually the Hamiltonian in this case. And this looks like the time energy uncertainty relation. But of course, X here is not an operator, is a parameter, okay? So we don't need to define a time operator for this purpose. So it looks like the number phase or the energy time uncertainty relations, but it's not the Heisenberg, does not correspond to a Heisenberg uncertainty relation. Now, let's go back to the spatial displacement using this formalism. Now you see the displacement of some initial state of the harmonic oscillator can be given by this expression here. This is just the position displacement operator. It's a unitary operator. It is displacing this coherent state here, say, or this squeeze state here. And P is the momentum operator. So the momentum operator is the generator of spatial displacements. If again we apply this expression here to find what is the operator H, well, we find that it's the momentum operator as expected, okay? It's the generator of spatial displacements. The quantum Fisher information in this case is proportional to the variance of this momentum operator, which means that the uncertainty using the Kramer-Rao bound, the uncertainty in the estimation of this displacement is bounded below by this expression. And again, this looks very much like the Heisenberg uncertainty relations between X and P, but it is not, because X is not an operator, X is a displacement. So this is not the Heisenberg uncertainty relation, it is the Kramer-Rao uncertainty relation. Now for a coherent state, we know already that the variance in the momentum is equal to the variance in the position. Again, I'm using h bar equal to 1. And if we replace this delta p square here, you find indeed that the variance in the position is bounded below also by 1/2. And that's the standard quantum limit. Furthermore, a coherent state is a Gaussian state, so it saturates the Kramer-Rao bound. So in fact, for the coherent state, this inequality here becomes an equality. That's also true for a squeeze state. You can show that the squeeze state is a Gaussian state. So again, a squeeze state saturates this inequality as well. But you see that for a squeeze state, you can play this game. We increase the variance in delta P because that's a stretching operation. And at the same time, we squeeze the variance in X. So this relation here, the same relation we get before, shows that by increasing delta P, so this variance in P here, we can get a better bound, lower bound for the uncertainty in the position, okay? So we can get a better estimation of the position. So this is now the precise statement of what I said before. A squeeze state leads to a better precision in the estimation of the position. This looks like the Heisenberg uncertainty relation, but again, just stressing that X is a parameter, it's not an operator. This is actually Kramer-Rao uncertainty relation. Let's go back to optical interferometry again. And we have the same system as we had before. Now we need to find what's the unitary operator that corresponds to a phase shift. And this is this operator here. You have here the number operator, and you can show that if you apply this unitary operator here to a coherent state, all you have to apply, you can apply to this expansion of the coherent state in terms of this harmonic oscillator eigenstates. Now, when you apply this number operator to a number state, A dag A gets replaced by N, And now look at this, you can put e to the I n theta together with alpha here. So this is just the coherent state alpha e to the I theta. So this is actually a phase displacement operator. And n, this number operator here, is the generator of phase displacements. From that, we can get the quantum efficient information for this case. So the quantum, you see the probe here, of course, is the field that we send through the interferometer. And the quantum efficient information is 4 times the variance of the photon number operator. And from that, we get the Kramer-Rao bound, which is given by this expression here. Okay, so you see the larger this variance, the better can be the precision. In fact, if you this is the standard deviation, right? The square root of the variance. So if you put it on this side of the inequality, you get this expression here. And again, this is a kind of number phase uncertainty relation. The better you know the number of photons, the worse you get you can estimate the phase. But again, this is not a Heisenberg uncertainty relation. This is a Kramer-Rao uncertainty relation, and we got it because we consider theta as a parameter, not because we consider theta as a phase operator. That's not needed in this case. So this is the standard limit in this case. It corresponds to coherent states. And since for a coherent state, the variance in the number of photons is equal to the average number of photons in the state, this expression here can be written like that, which is very similar to the one we had before, just by comparing two coherent states, except for this factor 2 here. So we find that delta theta is bounded below by this expression. This is the standard limit. We sort of gained a factor here, a factor 2. Okay? And that's telling us actually that comparing two coherent states, like we did before, is not the best way to estimate the phase. Okay? You see the advantage of using the quantum efficient information, that it may stimulate searching for a better measuring procedure. And in fact, there is a better measurement procedure other than comparing the shifted coherent state with the unshifted one. You just compare the shifted coherent state with a classical field that's called homodyny, okay? And then you get this factor of 2 here. Okay, so you see that knowing the quantum efficient information and knowing these bounds here could be a useful experimental tool for finding the best measurement to estimate a parameter. Now, if you use a known state like we did it before, you see the variance in the number of photons here is larger than before. Now the variance in the number of photons is equal to n squared over 4. So it's not proportional to n, it's proportional to n squared. And from that, by using the Kramer-Rao relation, we find this expression here, which is the Heisenberg limit in this case. Okay, so the larger the variance in the number of photons, the better will be this lower bound. So the smaller it will be, which means that you have the possibility of getting a better precision in the estimation of the phase. Now, you can apply all that to atomic or spin spectroscopy. Again, suppose you have a spin here in a state which I call state 1, that's spin down. And then I apply a radio frequency field to this spin and put its state in a superposition of two states, say 0 plus 1 over square root of 2. So the spin now is along this x-axis here. And now the spin, which is in the equatorial plane, undergoes some rotation due to some small magnetic field applied along the z-axis. Okay? So this state here becomes this state here. See the state, the spin vector has rotated towards this direction here. Now we have this state here, and we want to estimate this phase. And if we estimate this phase, we'll be actually estimating the small magnetic field that is applied to the spin. Now, how do we estimate it? Well, we could do measurements on this basis here, which is composed of this state plus the state with a minus sign here. And measuring on this state is equivalent to measurement of sigma x, because these are eigenstates of the x component of the spin. And indeed, if we calculate these scalar products between the phase shifted state and the original state, either with a plus sign or with a minus sign, That's a simple calculation. You find that this is equal to cosine square of phi over 2 or sine square of phi over 2. And from this, we can estimate the phase. Okay, so that's the procedure. You might ask, how do I measure sigma x? Well, use a Stern-Gerlach oriented along the x position of the spin. Okay, now there's another option. I can rotate now this spin here around the y-axis. So instead of being in the equatorial plane, the vector will be now in the zy plane. And now you measure the population. That means you measure the spin along the z-axis, and that will give me this expression here. And again, by measuring the probabilities of finding the spin in the 0 or the 1 state, you get information on the phase. Okay, so that's a way to do spin spectroscopy, and you can do much better than that actually by using entangled states. Now, I have gone a long way in my time now. Of course, we started a little bit later, so I have to see what I'm going to tell you now. Please, Daniel, advise me on the time, because I don't know how much time I have now, and I have to decide what to show you. Daniel?
You can still talk for 15 minutes.
Oh, okay, very good, great. So, so now I want to estimate a phase due to the interaction, say, of a spin with a magnetic field, and put it in a more general framework. I may say that one wants to estimate a small change of phase between states of a two-level system, any two-level system. And this would allow, as I mentioned before, the estimation, say, of a small electromagnetic field, or yet a transition frequency between these two states if you have a two-level atom. So we have two possible strategies. One is to do what I mentioned before. Just measure for each single spin. And we do that, say, by placing this spin, as I mentioned before, in the superposition state, letting the state undergo this phase shift, so we get this state here, okay, like in the example I showed you before, and then you measure the state in this basis of eigenstates of sigma x. Now, this phase shift here can be implemented by this phase shift operator. And I leave it to you to show that this is sigma z, it's the z component, it is Pauli spin operator. Now, if you apply this unitary operator to 0 plus 1, you get this shifted state here, okay? Another exercise for the students. In fact, this operator, which is in the exponent here, is 1 plus sigma z divided by 2, is just the projection onto the 1 state, okay? So if you are in the 1 state, you get a phase shift. If you are in the 0 state, you don't get a phase shift. That's what this unitary operator is telling me. So now you measure this final state on this basis, and this measurement, if you take this state as the state you are projecting, the measurement state, it's an eigenstate of sigma x, the answer can be yes or no. Is it in this state or not? Okay, so it's a 1-bit answer, yes or no. And you do that for each single spin in this ensemble. And now you calculate the Fisher information for that. Now we have two terms in the Fisher information because you have only two different measurement results, yes or no. So you can have the probability of yes is given by this expression here. It's 1 plus cosine of phi divided by 2, just calculate this projection here. And the probability of no, that means the probability of finding not in this state, but in the state with a minus sign here, is given by 1 minus PS, because you have only two possible results. So the probability of getting a no is 1 minus the probability of getting a yes. And this is given by this expression here. So this is cosine square of phi over 2, which I mentioned before. And this is sine square of phi over 2, which I showed in the previous slide. So this is a measurement of sigma x. And the Fisher information is given by the sum of the expression I had before for deficient information over these two possible measurement results. One has probability PS, which is given by this expression. The other has probability 1 minus PS. And if you sum these two expressions, well, you put them under the same denominator, you get this expression here. And now we use these values here, and this gives me 1. So you see, the deficient information for this kind of measurement is equal to 1. But you have here n experiments. So you should multiply this lower bound within the inside the square root by n, the number of experiments, and that gives me this lower bound for the uncertainty in the estimation of the phase. Since deficient information is here equal to 1, this lower bound is 1 over square root of n, and this is the standard limit in this case. Okay, so that's a possible strategy. The other possible strategy is not to deal with separable states, but with an entangled state of these qubits or the spins. And the entangled state can be written like that with a proper normalization factor. Say 0 to the n is just the product of spin states all in the 0 position. And 1 raised to the power n is the same thing. So this is a state 0, 0, 0, 0 plus 1, 1, 1, 1. Now, each state like this undergoes a phase shift. Now, since you have several ones together, each one has a phase shift of phi. Together, they'll have a product of e to the I phi, and this will be of n phi. Okay, so this is a phase shifted operator, and you already see an advantage of using entangled states here. You see that the small phase shift, if you want, has been amplified here. You have some n phi here. So an entangled state helps to amplify the initial phase shift. And that is very similar to what happened to the displacement in that experiment in Winans group from 2 years ago. You see, they amplified the displacement here by squeezing the original state. Here we're amplifying the phase shift by entangling the qubits. And now you can find what's the probability of finding this shifted state in the original state. So you make the scalar product between this and that, and the answer can be yes or not. Not implies that this state is not found here, but in the state with a minus sign. Okay, same thing here, with the difference that now we have an entangled state. Now we can again calculate the probability of yes, the probability of no. And the only difference between what we had before and we had now is that now we have this exponential with n phi instead of just phi. So these two probabilities are given by this expression here instead of these two. You have this n here. And now I can calculate deficient information as before. And if I do that, I find that, oh, this is wrong here, I'm sorry. I find that deficient information, oops. So I find the deficient information is given by 1 over square root of n. Okay, wrong here. Okay, so I'm sorry, deficient information is given to n, is given by n. Okay, because I'm differentiate this with respect to phi, and that gives me an n outside. So deficient information is given by n here instead of 1, and this lower bound now becomes the square root of n times n, which is equal to 1 over n. So that's the Heisenberg limit. So you see that if I use an entangled state, I get a better precision than if I use separate states. And I'm going to show you that even formally, this is completely equivalent to what we had of what we had for displacements of states. Now, another important comment is that projecting on an entangled state is not the only possible measurement. And this is important because you might ask, how in the hell I do that? How can I do this measurement on an entangled state? In fact, we can show that measuring on separable states gives them the same result. But the question is, I had these two kinds of measurement before, and the question is, can I do something better than that? So are these the best measurements? And now the quantum fission information comes to our rescue. We know that for the best measurement, the quantum fission information is given by 4 times the variance of the generator of phase displacements. And as I mentioned before, the generator in this case is given by this expression in terms of the Pauli operator. Now, since for that combination 0 plus 1 over square root of 2, this state that I call plus, we have this variance equal to 1 over 4, another exercise for you. Just calculate this variance in the state 0 plus 1 over square root of 2. That's 1 over 4. Then I find that the quantum fission information from this expression here is equal to 1. But you see, what we have just shown as the quantum fission information coincides with the previous result for the fission information. So that means that for separable qubits, the measurement of sigma x, as we had before, maximizes the fission information. So what we did before, measuring on eigenstates of sigma x was indeed the best measurement because it led not only to a fission information, but to the actual quantum fission information in that case. What about entangled qubits? Well, in this case, the generator of phase displacement is given by the sum here of generators for all these qubits. And I find now the variance of this generator in the initial entangled state, and that gives me n squared over 4. So the quantum fission information now is given by n, it's the square root of 4 times this variance, so it's equal to n, as I mentioned before. And the lower bound is given by then 1 over n. And this shows that the result I found before by looking at these measurements here, this is the best result I could do, okay, I could get. So the quantum fission information is useful for helping me to find the best measurement. I may have some intuition about what the best measurement is. In this case, I measured on this basis. In this case, I measured on this entangled state basis. But by calculating the quantum fission information, we may be sure that these are indeed the best possible measurements. Now, a final remarks. A simpler measurement also leads to the best result. I mentioned that before, but now I'm showing you how it works. In order to estimate the phase for the entangled state, I choose this product observable here, and the eigenvectors of this observable here are given by this expression. This is just a product of these combination states, 0 plus or minus 1. Okay, so this is a product state with eigenvalues plus or minus 1. Now, and then I leave it to you to show, it's a very simple calculation, that the probabilities of getting the eigenvalues plus or minus 1 are given by the scalar product, again, between the entangled states and these product states here, and that's given by this expression, which leads to this quantum fission information, which coincides with the quantum fission information and leads to the Heisenberg limit. So what this is showing me is that there is more than one kind of measurement that leads to the quantum fission information, fortunately. So we don't have to measure in an entangled state. That does not need to be our measuring procedure. We can actually measure on this product state, which is much easier because we can do independent measures on the qubits that are part of the entangled state. Now, since we are in a quantum information course and a quantum information school, I would like to express all I have said so far in terms of quantum logic gates. And I believe that many of you have already seen this in quantum information lectures or in working with quantum information. That's a simple way of expressing what I have just said. We have these so-called quantum logic gates. These 3 first gates here correspond to the Pauli spin operators. So they are given by these matrices here. Okay? And we also have the Hadamard gate, which is given by this expression. When we apply the Hadamard gate to the zero state, it gives me this expression here. So the zero state, if you want, is represented by a column vector, 1, 0. If you apply the Hadamard gate to this one state, you get this. So the Hadamard gate is the one which transforms the zero spin state into a superposition state. Also, you can have a control NOT gate, C NOT gate, which is represented by these matrices here, by this matrix here. And it's very easy to understand what it means. You have a control qubit and a target qubit here. If the control qubit is 0, it's the first one here, and the target qubit is 0, well, it remains like that. Actually, if the control qubit is 0, nothing happens to the target qubit. So if this was 1, it would remain 1. On the other hand, if the control qubit is 1, it changes the value of the target qubit. So 1, 0 becomes, for instance, 1, 1. Okay? So it's a NOT, 0 becomes 1, 1 becomes 0, but it's a NOT controlled by the state of this qubit. This C0 gate, therefore, is different from the previous gates because those gates affected just 1 qubit. This control NOT gate is a 2-qubit gate, and it's also an entangling gate. So if the control qubit is in a superposition of that, then you see if the target qubit is initially in the state 0, then the state 0 here does not change the state 0. The state 1 changes 0 into 1. So the final state is this one, which is an entangled state. Okay? Now you can also have a controlled Z. So that means you apply sigma Z or not, the Pauli spin operator or not, depending on whether the control qubit is 0 or 1. So that is represented by this matrix here. Okay, so these are the quantum logic gates. And now I want to discuss quantum optical interferometry, if you want, or quantum interferometry in terms of quantum information. So the things I did before to separable states can now be represented by this plot, this graph. And you see, if you initially state 0, that means spin pointing down or up, it depends on your convention. You have a Hadamard gate, so you produce a superposition of 0 plus 1. Then you apply this unitary operator, which involves a phase shift, if the state is 1. Then you apply again the Hadamard gate, which means that you transform the state around the in the equatorial plane on a state around the ZY axis, and then you measure the state. Okay, so just following this evolution here, the first Hadamard gate produces this state here, superposition of 0 plus 1. Then you apply the evolution operator, you get this shifted state here. And then you rotate the state if you want. You produce now the state in the ZY plane, which is given by this expression. So if you find the probability of finding the spin up or down, you get cosine square of phi over 2 or sine square of phi over 2. And that gives me information about phi. Since here you have n independent measurements, the uncertainty in phase will be bounded below by this expression here, which depends on the number of experiments you did. And here I have an example with just 3 experiments, but you can easily extend this to n cases. So this is what I did for separable states. Now let's look at the situation for entangled states. Now this is a little bit more complicated. So first, I apply the Hadamard gate to this 0 state, so I get the superposition state here, just for this spin or for this qubit. The others remain in the 0 state because I applied the Hadamard gate just for this first one. Then I have C0 gates here. Okay? So apply the C0 gate between the first spin and the second spin, and this one between the first spin and the second spin. Now you see, this first spin in this is in the 0 plus 1 superposition. So the zero state will be associated to the zero state here and here. So we have this expression, while the one state here will transform this zero into one and this zero here into one. So we get this entangled state here. So again, a C0 gates as entangling gates. So we produce now this entangled state, and now we will apply these unitary transformations to these entangled states. So I get this phase shifted state now with n phi instead of phi. And now I have this different measurement procedure, but which is very instructive in the framework we are using here. I apply the same operations I had there in the inverted form. So first the C0 gate, then the second C0 gate here, and then the Hadamard transformation. You see that this sequence here is just the inverse of the sequence here. And now I measure the state. And I leave it to you to verify. It's very easy because this undoes the entangling which was done before, and the H Hadamard transformation transforms the state on the equatorial plane onto a state in the ZY plane. So you measure the populations, and this gives me this state here. Okay? So again, if I measure the population of 0 and 1, so if I measure if the state is 0 or 1, the probabilities are given by cosine square of this or sine square of this, and you have here an amplification of the phase. Now remember what we did when we tried to amplify the displacement of the ground state of the harmonic oscillator, like in the paper in Science in 2019. It's the same thing here. We apply this sequence of transformations, we do it, and then we undo it. And by doing and undoing it, we amplify the phase. So this is also an amplification procedure, very similar to the one we had for the displacement of the ground state of the harmonic oscillator. So that also shows the power of the symbolic procedure of using these gates and these lines to represent quantum interferometry, because this kind of representation allows one to treat completely different systems in a similar way. You see, now space displacement becomes very similar to optical interferometry, right? Both deal with amplification of a displacement. So, and that's the beauty of quantum information, that you can deal with several different systems using the same kinds of transformations, the same kinds of symbols. And of course, here, just to emphasize this, because of this n factor here, I get now the Heisenberg limit in the estimation of phase. Now, I will just finish with 2 comments, but I'm not going to show you the applications of that because of time. We have done work in our group on parameter estimation with losses. And then the situation becomes more complex, but you know, it becomes also more realistic, because unfortunately, closed systems are very beautiful, but they don't exist in nature. So suppose we go back to the optical interferometer I had before, and try to use a Nun state, which, remember, the Nun state has a higher variance, larger variance in the number of photons, so it's better for estimating the phase. Now you see, if you have some damping here and some damping here, so we have photon losses in these 2 branches, then a state like n0 plus 0n over square root of 2 can be quickly transformed into the state n minus 1, 0, or 0, n minus 1. It depends on whether the single photon was lost in the upper branch or the lower branch. So, if you lose the photon in the upper branch, you know that you had n photons there before. Not you necessarily, but the environment knows that. And if the environment knows that, the state cannot be the superposition anymore. The environment knows now that the state is n minus 1 and 0. If a photon is lost in the lower branch, then the environment knows that the state is this one. And this state here does not give you any phase information, because it's a Fock state, it's a number state. So if you have some e to the phi here, when you take the square or the norm of the state, the phase goes away. So that's not a phase between two states, which generates interference. It's just a state of a single state. And you know that an overall phase of a state does not mean anything in quantum physics. So if you lose a single photon, the capacity of this state in estimating the phase is completely lost. And you know, if you have an average number of photons in this branch, the time for losing a single photon is equal to the damping time divided by the average number of photons, okay? Because it's much easier to lose a single photon than to lose n photons. So this is not a good state for estimating the phase if losses are present. Now, we can show that for small n, you can actually get more robust states that can be numerically calculated. Now, if n is very large, that becomes very, very difficult, and that cannot be done anymore. So that's my last slide. In our group, we have developed a method to estimate parameters in open systems. And that's based on an extended space approach. So this article in Nature is the proposition, contains the proposition of these general frameworks. And I stimulate you to read this article if you are interested in knowing about this method. And then it has been applied to several problems, optical interferometers, estimation of a classical force coupled to a noisy quantum mechanical oscillator, for instance, or the estimation of damping constants and temperature. And this one was interesting because, you know, if you want to estimate a damping constant, of course, you have to deal with an open system. Otherwise, you don't have damping. And if you want to estimate temperature, you are dealing with an open system, so you better know what kind of method to use. So this is a more recent paper done with, in collaboration with Girish Agarwal at the University of Texas. And I should say that for all this work here, my colleagues at the Institute of Physics of the Federal University of Rio de Janeiro were extremely useful. Actually, I learned a lot with them. So Bruno Escher was my PhD student. He's now a professor at the Institute of Physics. Matos Filho is a great friend and a great scientific colleague of mine. You know, we have had, I don't know how many papers together. Maybe I have had more papers together with him than with anyone else. And Ruiné really taught me a lot about this field, and I'm always learning with him. Nissim Zaguri was also a great collaborator throughout my academic life. He was my teacher of quantum mechanics before I had to leave the country. That was in 1969. And here, Camille Latuni was my PhD student as well, and we did this work on estimating a force on a noise quantum mechanical oscillator. What's the idea? And I'll just give you an idea. I'm not showing you any application. The idea is the following. Suppose you have a system in an environment, and the system is not a closed system. It's a system with noise. So given some initial state in some non-unitary evolution, then I just enlarge the state of the system. In other words, we consider an environment associated to the system. And this environment does not have to be a physical environment. It can be any environment we imagine. And you choose an environment so that after you trace out the environment, you get the reduced dynamics of the system itself. Okay, you get, say, the master equation for the system. So you have to choose an environment so that if you take it out, if you trace it out, you get the non-unitary evolution of the system. So in this extended space, you have a unitary evolution because the environment was added just for that purpose, so that you have a closed system. And there you have a unitary evolution. Now, if you have a unitary evolution, you are in the best of all worlds, because now I can apply the quantum fission information, which is given by the variance of the operator related to this unitary evolution here. And X is the parameter you want to estimate. So you apply now this unitary evolution on the full thing. This is called purification of the dynamics of the system. You go from a density matrix to a pure state, and you calculate the quantum fission information now for the whole thing. Now, the quantum Fisher information for the system alone can be written in the following way. That's the Fisher information of the system plus, say, the identity. These are all the operators active of the system, and I consider that on the environment, I operating with the identity. So I'm not doing anything to the environment, and I maximize this over all possible operations, measurements, say, on the system S. So this is the old quantum Fisher information we had before. You ignore the environment, you don't do anything to it, and you maximize it over all possible measurements done on the system itself. Now, this is the quantum Fisher information which we would like to know, but it's tough because it's not a closed system. However, this should be maximized. This should be smaller, actually, than the maximization of the quantum Fisher information for the whole thing. Why? Because now I'm dealing with measurements on the whole thing. So I'm getting more information on the parameter than if I measured on the system itself. So this Fisher information here, which I call C or Q, that's the quantum Fisher information corresponding to the whole thing, is an upper bound for the Fisher information, for the quantum Fisher information of the system itself. So that's a way to find upper bounds for the thing we want to calculate. Okay? Now, the physical meaning of this bound is that it leads us to the information obtained about parameter when the S plus E is monitored, which is usually a hopeless task. Okay, I recognize that. Now, of course, we are interested in the least upper bound because the least upper bound will be closer to the quantum Fisher information of the system, which we want to estimate. So again, that looks like a hopeless problem. We want to minimize this over all possible evolutions in S plus E. So first you have to find a good environment, and then we have to minimize this of all possible evolutions. So two problems: find the best environment and find the minimization. So we found in this paper, we showed in this paper, that this bound is actually attainable. In other words, there is always a purification such that this upper bound coincides with the quantum Fisher information. So finding this purification is like the Santo Graal for this case. That would be great, because then we would find the quantum Fisher information of the system. What does it mean this physically? This means that if we find this purification, then monitoring S plus E uses the same information as monitoring S alone. That means there's no more information on S plus E than there is on S alone. The information you get by adding these environments, very special environment, is redundant in the sense that it does not add anything to the information in S. So that's the method. These are some of the applications. I still have some slides for some of the applications, but I'm not going to show them to you because I'm worried about your mental health, and I don't want to sleep, to go in a deep sleep at the end of this lecture. So I'm going to stop here, and I will thank you for your attention. If you want to know about applications, just go through these papers here, and you'll see that this idea actually works. And it works very well. Sometimes, for instance, in this case here, estimating a force on a noisy quantum mechanical oscillator, we found out what was this best purification, basing on physical principles, physical intuition. On other cases, we did not find the best purification, but we found an upper bound which was actually very close to the quantum Fisher information of the system obtained numerically. And finding the upper bound was very interesting because we had an analytical upper bound, which meant we could analyze some physics of the problem. So stop here. Thank you very much for your attention, and I'm available for questions.
Thank you very much, Luiz, for a very beautiful lecture. I will open for questions now. If you want to ask your questions, you can turn your microphone on. Otherwise, we have questions written in the chat on YouTube. Then I will leave René to read them for you. But if any one of you want to ask a question, you can turn your microphone on and ask.
Okay.
Okay,
Okay,
then René, you can read the questions then.
Yeah, thank you, Daniel. Thank you, Luis, for this great presentation. So let's go for the question. First question here at Zoom platform is from Gabo. So he asks, in the paper by David Wineland about the amplification of the displacement, what is the goal of the paper? Is it the measurement of the displacement? If the answer is yes, how they separate the information about the displacement and the squeezing?
Very good. Okay, very good question, Gabo. Yeah, and we are dealing with this now because we are applying this idea to new ideas to that measurement that David Wineland said. So if you go to that measurement, and I think I'm going to share my screen again, okay, Gabo? Let me see if I can do that. Yeah. Yeah, you know, Gabo, this question you asked was a doubt we had here. And I was discussing this with Girish Agarwal. And we had precisely this question that you asked. So, okay, let me do this. Okay, so you see, that's the paper by them. So their aim was to estimate the displacement. And this was a very small displacement. So they said, okay, so we want to amplify it. And they amplified it. So for us, in terms of quantum metrology, you know, they did not use quantum Fisher information. They did not have this language. So we tried to apply this language to the measurement. In terms of quantum metrology, this was the preparation procedure. They squeeze this initial state, then they displace it. And because it's a squeeze state, in principle, that helps them to get a better precision. Now, then they go to the measurement of this displacement, and you can consider that all of this, the anti-squeezing operation, this is the displacement, okay? Now the anti-squeezing operation and then the measurement of the resulting coherent state is part of the measurement, okay? So if you want to find the quantum Fisher information in this case, you have to find the generator of the displacement operator, the variance of it in the squeezed state, which is this one, which is the original state, okay? And that will give you the quantum Fisher information. And then, of course, in order to measure this coherent state, they transferred the information on the vibrational state. You see, this is an ion. So they transferred the information on the vibrational state of the ion to the internal states. It's a qubit, it's a two-level system. And they measured this two-level system in order to find information about the displacement. Okay, so that was the idea. So again, this part here is the operation of displacement, which comes from, the squeeze state comes from here to here. And they want to measure this small displacement here. And this, from S dagger to here, is the measurement part. Okay, and they succeed in getting to the quantum Fisher information. They don't know that. Now we know. Only if the displacement is very small, and the reason for that, and we know how to do a measurement so that you get the quantum Fisher information for all kinds of displacements. So that's a research, that's an ongoing research.
Okay, thank you, Luis. Yeah, I didn't know how the process was there, right? Because the process, it looks like you have two parameters, the squeezing parameter and the displacement. But if you divide it in that way, it's much clearer now. Yeah,
that's it.
You.
Thank you for your question. It was helpful to clarify it.
Okay, thank you, Gabo and Luis. Let's go to our YouTube chat. Our friend Carlos Eduardo Souza, aka Cadu, is asking about known states. He firstly mentioned how complex is the step of production and characterization of a known state in a displacement estimation experiment, and then asks, would you be able to tell the value of n in the known state used in current metrology-oriented experiments?
Okay, very good, Kadu. Yeah, no, it's not easy to produce a photonic noon state. Okay, of course, when you look at the entangled state of qubits, that's a kind of noon state, but for qubits, you have n spins up and n spins down. Okay, so if you call the spins down 0 and the spin up 1, you have n ones and n zeros, and that's a noon state for spins. So for spins, you can do it, and the way to do it is the way I showed you in the graph. That schematic approach. You apply, Hadamard gates so that 0 becomes 0 plus 1 over square root of 2 of 0 plus 1, and then you apply the C0 gates, which will entangle all the 0 plus 1s, and then you get the state 0, 0, 0 plus 1, 1, 1. Okay, so with spins, you can do it, and that has been known, and that has been known in NIST, because they are interested in measuring small phases, small magnetic fields, okay, and have good clocks also, which have to do with this phase there. Okay, so now for photons, it's very difficult to do it. There was an experiment done in England, actually, on the noon state with n equal to 2. Okay, so 2, 0 plus 0, 2, it's easy to do. It works on an effect of bosons on beam splitters, which was found out by Mendel a long time ago. It's Hu-Mendel interferometer. And then you can get a state like 2, 0 plus 0, 2. Okay, so, but for a general number, higher number of n, it's very difficult to produce it. You can produce it conditionally, but then the probability of getting it is lower and lower as n increases. Okay, now, how do you get n? You do the inverse transformation. Okay, you do the inverse transformation and you count photons. That's the way to do it. And again, I mean, you use the idea of quantum amplification of processes. So you do the inverse process, and then you see how many bits you have in the zero state. Okay, so that's the idea.
Okay, great. Next question from Danielle Jonathan. Luis, how much is the quantum advantage sensitive to the noise in the system?
Okay, very good.
In the initial state and the measurement itself.
Sure,
is there
Daniel.
a role for quantum error correction or other similar techniques?
Yeah, okay, very good. Yeah, these are the slides I did not show you, but I'm not going to show you because it involves more time for explanation, but it's like that. Suppose you have an interferometer and you want to estimate a phase, and you have noise there. Okay, so you still look for the best state. What you can show is the following. As the number of photons increases, okay, of course, you won't have a noon state there because, as I showed to you, the noon state is a very fragile state. So you take another state, in that case, which just to give you some idea, just motivated by your question, Daniel, a noon state had that problem. If you take, say, a 2, 0 plus 0, 2 state, the loss of a single photon destroys the ability of the state to measure the phase. So you do the following. You build a state which has 2, 0, 0, 2, and 1, 1. Okay, 1, 1. So if you lose a single photon in that state, you still get an entangled state. Okay, so that's the idea. You have to introduce a 1, 1 there. And of course, if you have N0 plus 0, 1, you have to introduce lots of other states, so that if you lose a single photon, you still get a coherent superposition that will give you some information about the phase. Okay. Now, what we showed was the following: as n increases, for instance, in the optical interferometer, no matter how small is the dissipation, for sufficiently large n, you get the standard limit for the uncertainty in phase. Okay, so delta phi will be proportional to 1 over square root of n, no matter how small the losses. Okay, so if they're smaller and smaller, that means that this limiting upper number of photons will get larger and larger. But always you get the standard limit. And that means that, for many kinds of states, as you increase the number of qubits, noise becomes more and more of a problem. Okay, because going to the standard limit means that you go to the classical case. Okay, and of course that's the worry that we have on quantum computers, and that's why the quantum computers that are working now, they have what, 72 qubits or something like that. Okay, and they work with very low temperatures, so that the noise is very, very small. As we increase the number of qubits in quantum computers, people think, Google says that if you get to n equal to 100, something like that, you start to have quantum supremacy. Of course, they have already said that they have quantum supremacy in a paper published in Science, but that was disputed by IBM, right? That showed that with their classical algorithm, they could also get that result in a time larger than the quantum computer. But anyway, it was not impossible. So you need lower and lower temperature. So getting to the 100 qubit number, that's already a challenge, but I think it can be done. Now, if you want to get to 1,000, I think we'll have to wait for some time, Of course, we have also shown in some papers, including former students of mine, and that was work done by people who are here now attending this, like Rafael Chaves, Fernando Melo, Leandro Olita is not in Brazil now. So what was shown, for instance, one of the papers showed that that was with Leandro Olita and Antonio Assim from Barcelona, and Daniel Cavalcanti as well. We showed that, for instance, if you have some kinds of states which are called graph states, their resistance to noise is larger, okay, depending on the kind of entanglement you want to look for. So there are some entangled states that are more resistant to noise than other states. So GHZ-like states, 000 plus 111, are especially sensitive to noise. But you can have, for instance, graph states. I'm not defining them, but you look in the literature, those who don't know about them, they are more resistant. There's more resilience to noise. So that's what we have found. But in general, noise is really detrimental to, for instance, quantum computation.
Would you have to have an embarked quantum computer on every quantum sensor in the end?
Well, you don't. Yeah, good question. But actually, at the end, the results from quantum sensors are obtained classically. So actually, it's funny because this area of quantum information had at least 4 huge pillars. Quantum computation, quantum simulation, which is different from quantum computation, right? Quantum simulation is like having these analogic computers one had in the past, it was Feynman's idea. You can have quantum communication, of course, quantum cryptography, and quantum metrology. And I would say that except for these, experimental realizations by Google, some others as well, with a small number of qubits. IBM also has done something about it. Quantum metrology is the most successful pillar so far, because you are able to do things that indeed classically you cannot do. And you don't need a quantum computer to do that, but you need quantum physics, in order to measure, for instance, magnetic fields that cannot be measured classically with a precision that is much better than the classical precision, or measure the gravitational field with a precision much better than a classical, or even these accelerometers and gyrometers, which I find amazing. Of course, people who use submarines, unfortunately, they are used now for more for war than for peace, but they should be fun to use for peace too, right? Looking at the deep ocean. So submarines don't, with these quantum accelerometers and quantum gyrometers, don't need GPS. just because at each moment, how much the submarine is turning around or how much it is accelerating. So you just integrate that. And the precision is enough for getting away with GPS. That's also useful for regions of the world where the GPS doesn't work. So the airplanes can still go along their paths without GPS. It would be useful also for things like September 11. That GPS was turned off all over the world because it was controlled by the United States. So planes in Brazil could not fly. Now, with quantum accelerometers and gyrometers, they would be able to fly. You see.
Yeah, this is actually this idea was from I think in ancient China they had these north finding carts that were they had gyrometers that we could take with a cart with an ox, and they would then they would was spinning wheel and would. But this obviously is.
That's what we use today, Actually, explorers use that, the bussels. How do you call it?
No, but without compasses. It was
without compass, I say.
A spinning wheel to keep
Oh,
track
just a spinning wheel, right?
Yes.
Yeah. Very good. Yes. Right. Yeah, that's the idea, precise of the gyrometers, to use a spinning wheel. Yeah. Yeah, but if you think about it, it's amazing because it's from the 4 pillars. It's really the one which is more successful. Even quantum cryptography, of course, it's being commercialized already. But there are always some doubts about the security of that and this kind of thing. But quantum metrology, you just have them. You have these devices. Yeah.
Okay, we have time for one more quick question. Would anyone like to ask a question with their microphone on? Okay, so I myself have a question, if no one has.
Yes.
It's a basic question about the definition of quantum Fisher information. So you showed that the quantum Fisher information is a quantity which must be optimized, right? After the optimization of overall possible measurements, quantum measurements, we get the Fisher information, right? So my question is, does the initial state play a role on this optimization, or only the measurement itself? And the second part of the question is on the measurement, if I understood correctly, finding the right set of POVMs is the way to optimize it, right? Is it equivalent to say that we have to find the right basis?
Yeah, okay, good. So first question, yeah, the quantum Fisher information is obtained for a given initial state. Okay, so given some initial state, you want to find out what's the best measurement procedure. And let me give you just the example we commented here. We had two, when we consider entangled states of qubits, we had two possibilities. One was to have a separable state, and then we would measure sigma x for all states. And the other was to have an entangled state. And then one of the possible approaches would be to use as a basis an entangled state, which was not in the other case, okay? Another even simpler example, when I consider the displacement of the ion, the measurement which was done, which was actually the best, would lead to the best possible measurement, was the following. You apply an anti-squeeze operation, and then you measure the outgoing coherent state, okay? Now, of course, that's associated to the fact that you first made a squeezing operation, okay? So it is associated to the initial state, okay? So yes, it depends on the initial state, okay? Now, choosing the best measurement is analog to choosing the best base. However, one should be warned about the fact that they are not necessarily projection operators. They are POVMs. So it's more general than that. okay? So the mass measurement could not be just a projection, a von Neumann projection.
Okay, thank you.
You're welcome.
We have no more questions for now. Daniel Schneider-Tasca, would you like to say something before we close?
Yes, so, well, first, I thank you very much for this initiative, and I think it's very nice to see younger people, from my perspective, of course. I have the impression that when I go to conferences, I am seeing more and more younger people, But anyway, that's natural. But it's very nice to see this new generation of very good scientists getting the flag, and getting the flag and going on with this Paraty workshop, which was an excellent initiative. I think the results of that have been amazing to Brazil and other places also in the Americas, in the world, because the way it is organized, it's an excellent situation for discussing, for learning new physics, for discussing physics, for setting up new projects, new research projects. So I think, if you look at the history of this Paraty workshop, it's a very successful history. And I'm very glad that this is going on. And I congratulate you for raising this flag and taking the flag from the oldest generation, for the older generation. Okay? And I'm very happy with that. So I think, and especially for the people in Brazil, I want to say that, we have this very bad situation nowadays. But, there is a saying of a Brazilian poet, writer from the Northeast, that I think it's difficult, it's impossible to translate into English. I would first say it in Portuguese, and then I'll say it in English, but it will not have the same effect. It's Ariano Suassuna. He would write plays, and he was excellent. And he would say about, somehow ask him if he was optimistic or pessimistic about the future of the country. And he said, well, the optimistic guy is a fool. The pessimistic guy is boring. Now, I am hoping realist. And I'm very happy with this position. So in Portuguese, hoping realism means realista esperançoso. And he would say in Portuguese, well, o otimista é tolo, o pessimista é chato. Eu sou realista esperançoso. And it's funny because esperança, hope in Portuguese, people sometimes mix it up with waiting for, because, waiting for in Portuguese means esperar. And it was Paulo Freire, a very good educator in Brazil, that mentioned the difference between esperança and esperar. Because he who waits never gets there. Aquele que espera nunca alcança. But, esperançar is not coming from esperar. Esperança does not come from esperar. Esperança comes from another verb in Portuguese, which means, when in English, just to hope. In Portuguese means esperançar. And esperançar in Portuguese has a very interesting meaning, and I'm not sure there is something equivalent in English. Esperançar means actually not to wait for, but means to act, to be active in the sense of producing the future you want to happen. Okay? So what I can tell you, those who are in Brazil now and worried about the present situation, is that we have gone through terrible situations in the past and we have overcome them. But this is not going to come naturally, and that's why we should esperançar. In other words, we should act so that the future we want becomes a reality. And that's a message I want to leave with you. I think that by keeping on, by organizing workshops, even in the time of pandemic, and by doing good research in the universities, we are helping a new future to emerge. So for Brazil. So thank you very much, and let's go on. And don't get depressed, because the future is very close. It's very close. Elections will come next year, and who knows? Who knows what might happen? So I think that what we have to do is to keep working, keep going on, keep fighting for good science, for a different country that we have now. Thank you very much.
Thank you, Luiz. Vamos todos esperançar, então. Let's all act. And that's us who should thank you to lecturing us once again. I was very lucky to watch your lecture in 2007 in the first edition of the Paraty School. And now I'm watching it again. It's a great pleasure to have you teaching us quantum information for like almost 2 decades. Thank you very much. So I hope to see all of you in Paraty in 2023, our next edition. Give us a like if you liked the lecture. I'm sure you liked it. And subscribe to our channel for the next videos we're gonna post for you. So thank you very much. I will end the transmission to YouTube now.
Daniel, first,
Yeah.
I'm really willing to clap my hands because I see people using the emoticon to do it. So I suggest that everyone opens their mic and the video so we can give a salva de palmas.
Thank you, and to you too.